Now for lecture 18, the program is probably more clear. So the program was we extend or we expand or embed this real vector space into something which we call its complexification, and we understand how many of the properties of them are related. And now what we did in this lecture is we started to bring back knowledge that we had previously developed only for complex vector spaces. And why only for complex vector spaces? Because that's a space where polynomials always have roots. And then we saw that the definition of multiplicity of an eigenvalue, how it would make sense for the real vector space, and the parity. So real vector space, an operator on a real vector space, maybe it cannot have, of course, complex eigenvalues. It doesn't make sense, but once we complexify it, then it may have complex eigenvalues, and we can talk about multiplicity and parity, and the fact that the multiplicities add up to the dimension here. It says something about even the parity of real eigenvalues that a real operator can have. We have also defined the characteristic polynomial for a real operator only today. Okay? There was no characteristic polynomial for real operators before. Maybe you can argue, well, if we use the previous definition of characteristic polynomial, which would be the determinant of A minus lambda, the identity, or rather of Z times the identity minus the matrix of the operator, or whatever. If we use this as the definition, we would not have Cayley-Hamilton. Okay, it's something important to keep in mind. It's not just as a matter of being erudict that we are doing a different definition here. That is not just because we are trying to avoid the determinant. It's also because defining the characteristic polynomial by using multiplicity of eigenvalues, we have a theorem called Cayley-Hamilton. So we had Cayley-Hamilton for complex vector spaces, and now we have Cayley-Hamilton for real vector spaces, because we can now define what the characteristic polynomial is for a real vector space. And we know that if the real vector space has dimension n, the characteristic polynomial has degree n. Why? Because once we complexify the operator, we know that the multiplicities, they add up to n. Because, why? Because the vector space, if it's complex, then it's equal this direct sum of generalized eigenspaces, if you will remember, and so we can have this property. And all this that was true, we knew they were true for complex vector spaces. Now we have them for real vector spaces as well. So that was the point of complexification. This is the program we are running here. Now I can comment a little bit on some of the things some students said. One said we're working on complexification of matrices. Actually, it doesn't make any sense to complexify matrices. A matrix is a collection of numbers. If that collection of numbers are written in a funny form, written as a table like this, if those numbers happen to be real, how do you complexify them? Well, just treat them as complex. So it's a trivial matter to complexify matrices. We're not complexifying matrices here. We are complexifying abstract vector spaces over the field of real numbers. Also, we don't complexify properties of operators or spaces. The operators, they exist. The spaces, they have their properties. What we do is we complexify the object, and then we relate the properties of the complexification with the properties of the original object. Another thing is we did not introduce minimal polynomial today, and we did not say anything about the minimal polynomial on today's lecture, except for the fact that it divides the characteristic polynomial. Minimal polynomial was addressed in the previous lecture. And now there's a question, how do we connect real and complex knowledge? I don't think there is a definite, clear answer to this question. We are doing it, and as we do it, we get more and more the feeling of how it's done. So we can come back here and see about examples. We had multiplicity, parity, characteristic polynomial, Cayley-Hamilton's theorem, and we saw how to bring it back to real vector spaces by defining characteristic polynomial in a sensible way. And we saw linearly dependence or independence, they are related. We saw that how the matrix of a polynomial, once we complexify the matrix of an operator, once we complexify the operator, how they are related. Real eigenvalues, they are shared between an operator and its complexification, etc. So at this point, this would be the answer. We're doing it by examples, by one property at a time, one piece of that knowledge at a time. And some student pointed out, and it was very interesting, that some of us almost forgot that we had so far only defined characteristic polynomials for complex operators. So operators on complex vector spaces. And what I also want to express some disagreement with is what we did today does not depend so heavily on matrix representation. Matrix representation only simplified the proofs, and these are the proofs that I suggested that we follow during the lecture. However, if you see on the textbook, there is almost no reference to matrices. If you want it more complicated, you can not use matrices. Matrices only simplify the arguments. And finally, I don't think we're digging deeper into the properties of eigenvalues, Jordan forms, generalized eigenspaces, characteristic polynomial, etc. I don't think dig deeper would be the best description. What we're doing is we're translating our knowledge of complex vector spaces back into real vector spaces, because sometimes we may be interested in working on the real vector space itself, not a complex vector space. So this is what I wanted to say about the topics we learned today. Feel free to ask more questions in office hours or in the forum.